So today we'll talk about a somewhat different question in dynamic mechanism design. So far you heard about a couple of different problems, but related problems. One was maximizing the profits of one agent subject to the participation constraints of other agents. So and the issue there was extracting information rents. The other problem was the problem of optimal taxation, which is not exactly the same, but there was a similarity there that you want to reduce the information rents of the agent because it basically reduces the risk that the agent faces. So reducing information rents is similar to reducing the risk so that the agent's utility does not depend too much on his realized type. Okay, now here I want to talk about a different problem, which is the problem of social efficiency. And just to give you an example from public economics, because this is about public economics. So imagine you're managing a common resource like a public good, but it's a dynamic problem because the resource is evolving over time. So for example, the fishing stock. And so agents have private information about for example, the value for the fish or the technology for fishing. And the question is, how much fishing do you allow for each agent to undertake in every period with the view that this fishing will affect the future stock of the fish. And you could imagine there is some Markov process for the evolution of the fishing stock, which is controlled or dependent on how much fishing is going on. And in this situation, you would want to find some efficient mechanism for making these fishing decisions, so non-wasteful in the sense of budget balance. And also, if it's sort of an international agreement, then you would like it to be somehow self-enforcing so that you don't need to rely on some enforcement agency, but you can make sure that if somebody deviates from the agreement, then there will be some punishment available that the agents themselves could undertake. So basically, I will talk about my paper with Susan Nathan today, which looks at these kinds of issues. And so what we do in that paper, to give you a preview, first we construct a mechanism that is efficient, and that's really not so hard, as you will see. So it's a mechanism that gives perfect incentives to the agents. But the thing that's a little bit harder is to balance the budget. So, so the second step is to actually be able to construct a mechanism that is efficient, but also not wasteful in the sense that the sum of the transfers adds up to 0. Okay, you don't have to waste any money. And then we have a third step, which is under some assumptions, we'll be able also to make this mechanism self-enforcing. It's kind of similar to participation constraints in the static setting, as you will see. But the assumptions, of course, will involve some assumptions on the agent being sufficiently patient and also on the stochastic process being ergodic, and you will see why it matters. Okay, so just to give you a refresher, so we're going to basically build parallels to results that are, classic results in the static setting. So let me start with the classic results in the static setting. In the classic setting, the efficiency problem is defined simply as maximizing the sum of the utilities of the agents. So just to remind you, UI is the utility of agent I, depends on the decision and the state of the world. So the efficient allocation rule is the one that in every state of the world chooses an allocation that maximizes the sum of utilities of the other agents. Of course, the reason we look at the sum is because of the quasi-linearity assumption, so that this is exactly what equivalent to Pareto efficiency. Okay, and then this is implemented by the famous mechanism, the Vickrey-Groves-Clark mechanism, where so psi I is the payment that you give to agent I. This is the sum of the utilities of the other agents. plus some other term that does not depend on agent i's report. So this term hi, of course, this term does not affect the incentives of agent I. So the idea is sort of Pigouvian taxation idea that if you make agent I internalize the externalities he imposes on the other agents, that he will report truthfully because, well, of course, there's one important assumption for this, which is the assumption of private values. So the utility of agent I depends only on his own type, does not depend on the types of the other agents. Actually, with so if there is interdependence of values, then in general you will not be able to implement efficiency. Sometimes you still code, but that's a different, more complicated problem. Okay, so with private values, so the kind of the argument for why it works is that agent I basically gets the total surplus from his announcement according to the reports of the other agents, and it doesn't really matter whether the other agents are reporting truthfully or non-truthfully. He's getting so these payments make him get the total surplus calculated according to the reports of the other agents, and this total surplus will always be maximized if he reports truthfully. Okay, because that gives rise to the efficient decision. So that's basically the proof of this. Now, of course, this is a nice mechanism, but it doesn't balance the budget. So depending on the situation, sometimes you don't care about balancing the budget. For example, if you're running an auction and the auction has a surplus, that's not a bad thing. You can just, as an auctioneer, you will get the surplus. But in other situations, there is no outsider who will, everybody is a participant, and so you want to balance the budget among the participants. Okay, so, and unfortunately, it turns out that you cannot balance the budget if you force yourself to use dominant strategy mechanisms, and I think the first result was in a paper by Lafont and Maskin. So that means that we have to relax dominant strategy incentive compatibility, and we relax it usually to Bayesian Nash incentive compatibility, so that each agent will find it optimal to be truthful under the assumption that everybody else reports truthfully. Okay, so then if you do it, then you can, in Bayesian Nash incentive compatibility, then you can again implement efficiency using what's known as the expected externality mechanism, or the arrow, it's called AGV, which I think is short for Arrow and Depremont-Girard-Varey. The only thing I'm not sure is why Girard-Varey, no? That's right?
That's right.
But the question I have is that why Girard-Varey is one person and gets 2 letters, and Arrow and Depremont are 2 people and got only 1 letter.
It's a mystery.
It's not fair, but that's a standard name. So the point, okay, so the way the mechanism works is that instead of, okay, so first to understand the mechanism, look first at the second line. So gamma I of theta I, so I will call it the incentive term of agent I. So this is the term that's designed to provide incentives to agent I, and this term depends only on his own report. That's important. And so it's calculated as the expectation of the sum of the utilities of the other agents, the expectation taken over the possible types of the other agents. So we are not using the reports of the other agents to calculate this. Instead, we are just taking, kind of plugging in all possible reports, drawing them from the right probability distribution, and taking the expectation. And that's why this term depends only on the report of agent I. Okay, so the idea is that on expectation, if agent I believes that the other agents are reporting truthfully, then it gives him exactly the same incentives as if he was faced with the Vickrey transfers, and he will report truthfully to maximize the total surplus. Well, of course, it's still not budget balanced, but now budget balance is not a big problem because this incentive term of agent I depends only on his own report, does not depend on anybody else's report. That means that we can ask this term to be paid by the other agents without affecting the other agents' incentives. So now if you look at the previous line, that's how the total transfer is constructed. There are many ways of doing it, but for example, this way, so agent I is getting his incentive term, and then he contributes to pay the incentive terms of all the other agents. Let's say equally. It doesn't have to be equally, but for simplicity. And so this way we balance the budget. and agent I really doesn't, his incentives do not depend on the second part, and the first part gives him the right incentives on expectation. Well, there's one important assumption here. Actually, there are two important assumptions. So probably still keep the assumption of private values, but also we assume that the types of the agents are stochastically independent for this to be true. And actually, I remember this was, Eric gave me this question on my oral exam at Harvard, whether this assumption is important or not, and I didn't give the right answer. I still passed. So now at least I learned my lesson. So I don't know, I probably don't remember this, but you know, in my memory, it'll be, sounds plausible. Okay.
There are some cases where you can do it.
Sure.
With correlation, but again, not as general.
Yeah, yeah.
But if you have a dominant strategy mechanism with interdependent values,
Yeah.
then you can use the same trick.
You could, as again, assuming stochastic independence.
Right. So
Yeah.
private values is important only insofar as it's specified.
Okay, so good point. So actually, what I didn't write, but I could have written is, and actually I will show it more generally also, exactly what you're saying is that if you have a dominant strategy mechanism and you have stochastically independent values, then you can do this kind of expectation thing to balance the mechanism. And you don't need to assume private values for that. So the way it breaks out is that you use private values to make sure that you have a dominant strategy mechanism, and you use independence to balance the mechanism that you already have. So that's, I could have done it, and that's actually how we'll do it in general. Okay.
But you're not going to get dominant strategies without private values anyway.
Well, sometimes, in some
Well,
cases.
you can
Yeah.
get Bayesian equilibrium. You can get ex post equilibrium with.
Oh yeah, sorry.
But not.
Yeah, no, that's right.
Not dominant strategies.
Yeah, that's right. So yes, so with ex post equilibrium is enough for this, but exactly, I should have said the dominant strategies is too strong when you don't have private values, but you can weaken it to ex post equilibrium, which is still pretty good. Yeah, when you can, yeah, well, but then it's not always feasible, but sometimes it is.
One-dimensional single crossing case.
Yeah, just like in your QGE paper with this Gupta. Yeah. Okay, so now that we recalled all the static mechanism design, now we go to the dynamic setting, and so here I'll start with an example to show why it doesn't just easily extend, why you need, there's this extra complexity, and the extra complexity in the dynamic setting comes from, just like we talked about before, it comes from the agent being able to have more complicated deviations, and in this case also the agent learning information over the course of the mechanism over the types of the other agents, which increases the set of his deviations. His deviations can be conditional on that information, and that can undermine the incentives in some mechanisms. Okay, so this is a kind of the simplest example of that problem. Suppose you have two agents, a buyer and the seller, and in the first period the seller learns his type, and the buyer at this point doesn't have any private information, and he buys some quantity x1 from the seller. Then in the second period the buyer learns his type theta b, and we assume the seller's type doesn't change, so just it's persistent to make it simple. And then there is a second quantity, the second trade, where the buyer can buy quantity x2 from the seller. Okay, now the payoffs would be, to make it simple, in the first period the buyer has value 1. He doesn't have private information in the first period. His value for trade is just 1. In the second period his value for trade is theta b, where theta b is his new private information. And the seller's cost in each period is quadratic, so x will be a continuous variable, and the seller's cost will be just quadratic 1/2 x squared divided by his type in each period. Okay, so efficiency is easy to calculate. In the first period the efficient decision is just equal to the seller's cost, but in the second period it's a product of the two types. Okay, so you can see that the issue here is that this information revelation in the mechanism, where the buyer, he will know, there's no way to hide from him in the first period how much he consumes. So, and from his consumption in the first period, he will necessarily infer the seller's type. And he can make use of this information on his deviation. So just as a first attempt, let's try to use the static expected externality mechanism and see how well that works. So this is a static expected externality mechanism in this setting. So the incentive payment to the seller will be a function of the seller's announcement, which is the expectation of the buyer's value over his possible types. And the incentive payment to the buyer is a function of his announcement, the expectation of the seller's cost over the seller's possible types. So this will work perfectly if the seller and the buyer report their values simultaneously. So that will give them incentives to report truthfully. And you can balance the budget, obviously, simply by having the total payment to be the difference of these two payments, so that each agent pays the incentive, makes the incentive payment to the other agent. And then so the buyer, given his priors about the seller's cost, will have no incentive to manipulate this mechanism. But the problem is, of course, that after the buyer doesn't know his type until after the first period, and then he already observed his consumption, so he already knows from his consumption he will infer the seller's cost, and this will give him incentives to lie, because the payment will just be calculated according to the expectation of the seller's possible costs, but the buyer will actually already know what the seller's true cost is, so he will not be charged the right externality. And so depending on whether the seller's realized cost is above or below the expectation, he will have incentives to understate or overstate his type. Okay, so this extra information revelation, of course, if you could hide this, the buyer's first period consumption from himself, then there would be no problem. But the problem is the information disclosure. Okay, so then you might say, well, let's change the mechanism a bit, because the buyer already observed this information, the seller's cost. So instead of the expected externality, let's give him an incentive payment that equals to his true externality on the seller. He already knows what it is. So calculate, using the seller's report, calculate the true externality and charge it to the buyer. So that will fix the buyer's incentives, all right. But now that will change the seller's incentives, because you calculated based on the seller's report. So it now depends on the seller's report. And so the seller will have an incentive to misreport to manipulate this term. Okay, so how do we solve this problem? Well, instead of keeping you in suspense, I will show you a very simple trick that actually turns out to solve this problem. Okay, so instead of, here's a way we propose to calculate the payment to the buyer. So now it will have two terms instead of one term. Okay, so the first term will be the actual cost of the seller given what he reported. But from here, we will subtract the expectation of this term. The expectation is taken over the possible reports of the buyer. Okay, so this is the expectation of this term. Okay, at this point, you may not know why. I'll explain in a minute why it works. Okay, so this is the expectation of the seller's cost given the seller's report, but over all possible reports of the buyer. Okay, so how does this work? Well, think about the buyer first. From the buyer's viewpoint, the second term does not depend on his report at all. So adding the second term does not affect the buyer's incentives at all. So it's the same as if we were here, which would obviously, just like in the Vickrey in the VCG mechanism, it will give him incentives to be truthful. But it turns out that by adding the second term, we also fix the seller's incentive problem. So we'll eliminate this manipulation incentive that we had here. Okay? And the way it works is that if you think now, what is the seller's expectation of this difference? Now, if the seller believes the buyer to be reporting truthfully, then the seller's expectation of this difference will be exactly 0, no matter what the seller reports. Okay? So the seller's misreporting does not affect the expectation of this term, and therefore it's fine. We can ask the seller to make this payment to the buyer without affecting the seller's incentives and expectation.
the seller is completely indifferent among all.
Yeah, no, but he has another payment. So there will be the incentive payment that, yeah. So the point, so there will be two terms, okay? So there will be the incentive payment that will give him the right incentives, and there's this payment where we only worry about not violating, not changing his incentives with this payment. Yes, right. Okay, so here, so the total payment will be the difference between these two payments, right? So that the seller will get his incentive payment, and he will make the incentive payment to the buyer. And so the idea is that each incentive term gives the right incentives to one party without changing the incentives of the other party. That's the same idea as in the AGV mechanism, clearly, but of course the complication here is that you need to construct these terms in a somewhat more sophisticated way, because in the AGV mechanism, it's obvious, because incentive payment to me depends only on my report, so it's completely obvious that it doesn't, affect the incentives of the other people. But here, the incentive payment to the buyer depends on the seller's report. But it turns out on expectation, it's such a way that the expectation of this is still zero, no matter what the buyer reports, so it doesn't change the incentives, no matter what the seller reports. So, okay, so this is the extra complication, okay, that arises in the dynamic setting. Yeah.
So if you use your envelope approach,
Mm-hmm.
would you also get this?
Well, so I think you would get this, but actually it turns out this is more general than the envelope approach, as you will see, because it will not actually depend on the size of the type space. So it will not depend, just like the BCG mechanism and the AGV mechanism, it will work for arbitrary type space. It could be large or small, it could be discrete, multidimensional, so that while the envelope approach, of course, it requires continuous type spaces and so on, so it's more restrictive. I think what you so the envelope approach, although it only works on expectation, so it will tell you kind of like I think probably what you're referring to is the payoff equivalence result. So it will tell you that if you want to give the right incentives on expectation, it has to look in expectation like victory, sort of, right, to each agent. But it doesn't tell you how you can balance the budget. So the challenge in balancing the budget is to kind of ensure that you have the right marginal expectations for each agent, but at the same time, it has to balance the budget in every state of the world. So you have to spread these expectations over states of the world in a way that the budget is always balanced over all possible states of the world. And it's not a trivial question of how to do it, because you sort of have these constraints that the expectation for each agent over the other agent's reports is given. It's given by the envelope formula. Okay, and this is a constraint you have to honor, but you also have to honor the constraint that for every realization, the payments have to add up to zero. And that's not a non-trivial problem of spreading them. Okay, so here, we're not claiming that, of course, this is not the only way of solving the problem. So just like in the static setting, the expected externality is not the only way of solving the problem. There are probably many ways of doing it, but that's sort of the simplest way we could think of. But there are many other ways of spreading this, spreading the payments in some way to ensure that the expectations are the same. Okay. Okay, now here's the general dynamic model. Basically the same model as we had before. You have a countable infinity of periods. In each period, each agent privately observes a signal. So agent I in period t observes a signal theta it. But it is more general, as I said, in the sense that we are not making any assumptions about the type spaces of the agents. It could be completely general. Okay, the agents send simultaneous reports. Each agent makes a... So by the way, so here, just to make it a little more general and interesting, so we allow moral hazard as well, so that agents can make private unobserved decisions. And of course, you can anticipate probably that we can only sustain efficiency when the moral hazard doesn't have externalities. So this decision could be like increasing my value, but if it has externalities, then in general you will not have efficiency, right? But it allows for kind of self-investments, if you wish, where investments are increasing maybe future values and things like that. Okay, so XIT will be the private decision, so non-contractible, not observable private decision of agent I. And also, the public decisions, the decision that can be enforced by the mechanism, will be denoted by 0. So 0 is the agent 0 is like the the enforcer. So x0t is the public decision, and this enforcer will also make transfers payments PIT to the agents. Okay, the histories are denoted using subscripts, just as before, and also for decisions. The technology, just as before, the types in period t are drawn from some distribution that depends on the history, and we'll make assumptions on this later. So it allows for things like learning by doing, habit formation, allows for investments, for kind of private investments in values like self-investments and so on. And the payoff of agent I in general, some function of the whole stream of decisions and types, and plus the net present value of the payments. And you can, well, basically without loss of generality, you can, almost without loss of generality, you can spread the utilities of function of the stream into the sum, into kind of the flow utilities, but each flow utility can depend on the whole history. Okay, and basically, okay, the delta is a discount factor that's between 0 and 1. But when I say without loss of generality, there is some assumption of continuity at infinity that makes it possible, sort of a bit similar to what we had before, where if you have a capital U, a function of the streams that is Lipschitz, in some formal sense, Lipschitz continuous at infinity, so does not depend much on the distant future, then you can spread it into this flow payments in this way, where the future utilities here will actually make a somewhat stronger assumption that the utilities are uniformly bounded across periods, so that kind of the future becomes unimportant because of discounting. Yeah.
So the AGB trait given the dominant strategy mechanism is not restricted to the efficient.
Right.
Okay. So I guess that's what I was. So
Yes.
if you know that you can implement something given your envelope approach,
Mm-hmm.
does the insight that you provided here of taking kind of the average,
Yes.
does that also apply?
Yes.
Okay. So you.
So that gives you one. Okay. So yeah. So there will always be. So we call it the balancing. There will always be one way of balancing a mechanism.
So efficiency is not critical now that you understand what you can implement.
Yeah. Well, there are, efficiency is critical for one thing, and stochastic independence is critical for the other. So there will be two results. Yeah. And so I am breaking it up just exactly the way you are describing. So you will see it will be broken up into two results that are almost independent. Okay. Okay. So by the way, so here with finite horizon, this continuity, then there's really no restriction on utility. Okay. Now, so we'll look at direct mechanisms where the decision plan tells you in each period what decision should be made as a function of the history. So the decisions here we have public decisions, which is what the mechanism can enforce, that are indexed by 0, so chi 0t, and then chi it. These are recommended private decisions. So they're recommendations. So the mechanism will give recommendations to the agents, but of course you have to ensure that the agents don't disobey those recommendations, because nobody will observe whether they actually follow the recommendations or not. So given a decision plan that induces chi, that induces stochastic process mu, depends on chi in general, on the states. Uniquely defined as a technical issue. And as we actually discussed even when Sergio was here, so we do allow for correlation, some kind of correlation between this, individual agents types, but this correlation can come only through the public decisions. So we'll see where it matters. Okay. So the transfers. Okay, so they're functions of history, and we will also look, the little size will be the flows of the transfers, and we'll look at the present discounted values, capital size of these transfers as well, which in some sense, for incentive purposes, agents only care about the present discounted value. That's really what we mostly look at. But so we assume that the transfers, well, some version of spreadability, we just assume that they're uniformly bounded, which ensures that there is no funny things going on at infinity. So, and budget balance means they add up to 0 in every period, and Yeah, for every state of the world. Now, what about information disclosure? So by the way, in general, information disclosure matters in these mechanisms. And something that maybe I forgot to say last time is that when we looked at sufficient conditions for implementability, so the kind of the version of the weak monotonicity condition I said, it said that you can implement the mechanism without information disclosure with kind of minimal information disclosure, where the minimal disclosure means you observe only your own consumption. While, for example, a stronger condition of ex post monotonicity would allow you implementation even with full information disclosure. So here, in general, disclosing less will, of course, make it easier to satisfy incentive compatibility. As long as here the agents have private actions, you have to disclose enough. You have to at least tell them what actions they're supposed to make. That's sort of the minimal information you have to disclose. Well, in this, for the mechanism we'll consider, actually, we will show that even with full information disclosure, you'll have incentive compatibility. So even if the agents make all the reports publicly, you will check incentive compatibility, then obviously it will be preserved if agents are shown less than that, as long as they're shown, they need to be shown enough information to choose their private actions, but anything between that and full disclosure will preserve incentives for them. Okay, but as I said, so for profit maximization, sometimes you require imperfect disclosure, but here you can have full disclosure for efficiency. Okay, so the strategies, so of course, the strategy in general, it's a complicated animal because it also has to specify what the agent does following a deviation. But for us, it will be convenient to actually only look at what the agent does on path, and we call it reporting plan. Okay, so supposing he has been truthful, okay, so what is he going to do next? So if he was reporting truthfully, and his reports to theta I super t, these are kind of his reports in the past, which we assume were truthful. So his true type is equal to his reports in the past and his current type. And these are the reports of the other agents that he has observed. So what is he going to report today? So this is the reporting plan. It's not quite a complete strategy because it doesn't say what he will do after lies. And similarly for the private actions, what we call alpha IT, this is what private action the agent will choose given that he reported truthfully, given his current type, and given the reports of the other agents that were disclosed to him. Okay, well, it turns out given our proving approach, we will not really have to worry about what he does off path. So kind of in the normal form view of the game, we are not going to do it using one-stage deviation principle or anything like that. We'll just do it in the normal form of the game where, you know, this is the strategy, and then he can deviate. He can have a multi-period deviation to a different strategy, okay? And this is, and then it's enough to look at this kind of on-path behaviors, and we will be sustaining strategies that are truthful obedient. Truthful obedient means that everywhere on path, so when he has been truthful, he will keep being truthful, and so and he will be obedient as well. He will choose the right action. Okay, so then we say mechanism is Bayesian incentive compatible if truthful obedient strategies form a Bayesian Nash equilibrium. So that's one solution concept, and sort of the easiest solution concept to work with. But you can refine it a little bit. So, for example, we talked about ex post incentive compatibility. So here we cannot get quite ex post incentive compatibility, but we can get something that's within period ex post incentive compatible. So this says that you would remain, you wouldn't want to deviate even if you learn something about the other agent's current signals. So of course you always, because it's full disclosure, you learn something, you learn the other agent's previous types, previous signals, but also suppose you can spy on their current signals before they send their reports. And so within period ex post incentive compatibility, we'll make sure that even this spying will not change your incentive to report truthfully. Yeah?
But in the buyer-seller example that
Mm-hmm.
you had before, the buyer's signal came afterwards.
Yes.
Okay.
Mm-hmm.
It wasn't concurrent.
So there it didn't have any force, this restriction. Yes. Yes, but if it's a simultaneous reporting, then it would have some force, so that it would be a little bit stronger than. Yeah.
In the arrow array mechanism.
And it doesn't hold.
Doesn't.
Yes. So basically, our version of the VCG mechanism will satisfy it, but our version of the AGV mechanism will not satisfy it. Yes. So just there's no magic here. It's just okay. And then, even though we just formally will do Bayesian Nash, but it's not so hard to ensure a perfect Bayesian equilibrium here. Of course, in general, once an agent lied, he will want to lie, so because it's such a general environment. There is no, there's no reason why he should remain truthful. But basically, as long as you give him some reasonable beliefs and complete his strategy of equilibrium in some way, it will form a perfect Bayesian equilibrium. So under some assumptions, even for example, finite types, we construct on-path beliefs by Bayes' rule, off-path beliefs in a way that's kind of similar to last time, where the agent is not learning from his own deviations, and the complete strategies to be best responses, and then we can ensure that it all sticks together as a perfect Bayesian equilibrium. But just for simplicity, we'll just focus on checking that we have Bayesian Nash equilibrium. Okay, so this is kind of how we separate the results. So the first result is kind of the equivalent of the VCG mechanism. And actually, it is very simple. Well, you don't need to worry about budget balance. So first, let's define what we mean by efficiency in the setting. So efficiency is maximizing the total expected surplus, where of course the capital uses are all intertemporal utilities. So in some sense, the expected present value of the total surplus, this is what it is, given. So this depends on the decision plan. So you choose the decision plan that maximizes this expectation. So in general, this is some kind of dynamic stochastic programming problem, and we are not solving it, but we're just assuming somebody gave us the solution. Okay, somebody like Emmanuel or Oleg, who are good at solving dynamic programming, can give us a solution. Okay, so we just take the solution as given, and then to implement it, we can do it very easily by having this kind of VCG transfers, where in every period, agent I is getting a payment, which is the sum of the utilities of the other agents. So obviously not budget balanced at this point, but we can check incentives. So we call it the team mechanism, because in a sense, these transfers make each agent internalize the total surplus, so they become a team. Okay, and this is a simple result. So here you assume private values. So what private values means in this dynamic setting is that each agent's utility does not depend on the private information of the other agents, meaning does not depend on the private types of the other agents or on the private actions of the other agents. So under the assumption of private values, the team mechanism is Bayesian incentive compatible, and a little bit stronger, it's this within period ex post incentive compatible. Okay, and so the proof is straightforward. So because we have private values, when agent I thinks how he can affect his payment, so the only way his private behavior or types affects his payment is through the public decisions that he induces. So this is the only way he has an externality on the other agents. Okay, so therefore, even if he deviates, no matter what he does, he can lie or disobey the mechanism, but he will get a total utility plus payment. He will be exactly the total surplus. Okay, and also, of course, any deviation will be also, it will give rise, in a sense, every deviation will give rise to a different decision rule. But whatever, so he can induce a different decision rule, but it will still have to be an observationally feasible, a measurable decision rule, because it can only be based on what he has observed. And even if he managed to spy on the other agents in the current period, it will still be observationally feasible, because the mechanism, would be able to do the same thing. Okay, and then because we assume that chi star is already maximizing the expected total surplus, that means that he will not be able to find any deviation that will be profitable. Okay, so as you can see, it's kind of simple extension of logic of the VCG mechanism. Okay. Any questions? Now, of course, the problem with this is the payments. So they could be pretty big. If everybody has to pay the total utility of the other agents, so you'll start worrying about how can we reduce the payments. So there is a paper by Bergman and Valimaki that I think it's called the dynamic pivot mechanism, where they sort of try to bring down the payments, just like in the static VCG mechanism. You have the second term, which is hi of theta minus I. It's a function of the reports of the other agents. And you can play with the second term to try to reduce the payments. But if you reduce the payments too much, then agents might refuse to participate. So there's sort of some minimal payments that you have to make to satisfy participation constraints, and they work out a mechanism that has this feature. Okay, but that's a separate topic, so I'm not going to talk about it. So remark on ex post equilibrium. So we can satisfy some kind of within period ex post incentive compatibility, but true ex post incentive compatibility means that you can look into the future. And of course, if you can look into the future, then you generally would want to deviate, even if you just have one agent. If this agent can look forward and know the future, he will deviate because he will be able to make better decisions. But in some cases, so you can imagine some cases in which looking into the future does not help. So for example, where the optimal decision rule is myopic, in other words. So this is an example where decisions don't affect future types and you have time separable utilities. So then in some sense, it's not a dynamic programming problem anymore, because it's enough just to make myopic decisions. There's some dynamics, but it doesn't affect that optimal decisions are easier. In that case, you can have a truly ex post incentive compatible mechanism. Okay, but now we get to the more interesting question, which is how, yeah?
So the difference between expected maximizing expectation and maximizing the vector is just the measurability condition?
Well, if measurability condition means that you cannot condition on things you haven't observed yet.
Right.
Yes. Of course, if you can condition everything, then you can do it.
So this is sufficient condition so that if you do it.
Yeah, this is sufficient conditions for measurability not to be binding. Which, okay, it's of course very restricted class of problems. So maybe I shouldn't push it too much. Okay. All right. So now balancing the budget. So that's more interesting part. And actually, as Ron already was talking about this, that you don't really have to start with a team mechanism. You can start with any mechanism that's Bayesian incentive compatible and balance a budget in that mechanism. So it doesn't matter. As long as it's Bayesian incentive compatible, we can work with that. And we'll show how to balance the budget without violating this incentive compatibility of the mechanism. Okay, so remember, so if the mechanism gives this transfers little size, so little size, how the transfers of the flows of transfers, and we will also use the present discounted value of the transfers, the capital size. So using these present discounted values of the transfers, we construct the new transfers, which we call the balanced transfers. So there's superscript B, so psi B will be the balanced transfer. So this is a new mechanism with new transfers. And they're constructed on the basis of the original transfers in the following way. So this is there's a formula, so I'll try to explain it. It looks a bit complicated, but the general idea is similar to the expected externality, where so the total transfers to agent I will be his incentive term. So gamma is the incentive term. So gamma IT is the incentive term to agent I, incentive payment to agent I, and then he will be making the incentive payments to the other agents, or sharing equally in the incentive payments to the other agents to make sure that the mechanism is balanced. So then just looking at the first line, it should be clear that you have a balanced budget, because the way the payments are made. And then the second line is how do you build the incentive payment. So the incentive payment to agent J in period T will be calculated as the difference of difference between two expectations. Okay, so the second expectation is the agent's expectation of the PDV of the transfers in the original mechanism in the beginning of period T. So mu T means that calculated in the beginning of period T when everything before period T has been observed. So this is the second term. And the first term is the expectation of the same thing, but now it's updated based on the signal observed by the agent in the current period. So this difference is basically by how much the new signal, the new report in period T, affects the agent's expected present value of the payments in the original mechanism. Okay? And the delta minus T is basically because you want to bring it bring it into the future. Or bring it, not to period 0, so that everything will have to be in the units of period 0. Okay? So is clear what it means? Okay, it's a bit of notation, but the general idea is very simply how the agent's current type realization changes his expected present value of what he was supposed to get in the original mechanism. Okay, and that's what I said. Given that we already know all the history. So budget balance is already obvious from the first line, but the theorem is that assume independent types. Here, this is where we make the assumption of independent types. But what does it mean in the dynamic setting? It means that conditional on the public decisions, the private information of agent I does not affect the distribution of the private types of the other agents. So through public decisions, I could still affect the private types of the other agents. For example, I could, if I am a buyer and I report a higher value today, that I get the good, so the other agent doesn't get the good, and that might affect his value in the future. So that's okay, because this fact that I stole the good from him is a public decision. It's a public decision, but there's no direct effect of my type on his private information. Okay, so assuming independent types, then starting from a Bayesian incentive compatible mechanism and applying this balancing, you get another Bayesian incentive compatible mechanism. So for example, you can start with a team mechanism, and then the corollary is that with independent types and private values, the balanced team mechanism is Bayesian incentive compatible. But as you can see, in general, you can start with any incentive compatible mechanism, and then you don't have to assume private values for this result. So that's how it's broken up. So this result only requires independent types. In itself, it doesn't require private values. But the corollary requires both independent types and private values. Okay, and now I will sketch. I'll sketch the proof. So how does it work? So this is, again, I rewrote the incentive payments to agent J. Okay, the incentive payment to agent J, okay, multiplied by delta T to bring it into the present value. So this is the difference between two expectations. The second expectation, so we denote by gamma minus. So the first term we denote by gamma plus, and this is gamma minus. So this is gamma plus minus gamma minus. Okay, so the gamma minus term is the expectation of this PDV in the original mechanism given before the start of period T, and this gamma plus is this expectation updated based on the agent's current report. Okay, there are two expectations of the same function, just as I said, that the only difference is that they use different information. Okay, and there's two claims that give you the proof. So the claims are the following. So suppose agent I deviates, but he knows that the other agents are truthful and obedient. Okay, so the first claim is that if agent I deviates and the other agents are truthful obedient, then the expected present value of agent I's incentive terms. So expected present value means when you add them up over time and take expectations, then it will equal up to a constant to the expected present value of the payments in the original mechanism. So in other words, his own incentive term on expectation will give him exactly the same, even if he deviates. When he deviates, he'll get the same expected present value as what we would get in the original mechanism from the same deviation. Okay, so that's why we call it the incentive term, because this term gives the right incentive to agent I. But what about the incentive terms of the other agents? Well, the expectation of those incentive terms will have to be 0 also, no matter how agent I deviates. So that's why those terms can be safely paid by agent I without affecting the incentives of agent I to do deviations. Okay? So these are the two claims that we have to prove. Okay. So now I will actually kind of sketch how the proof goes. So let's start with claim 2. So claim 2 says that when agent I deviates, his deviation, no matter how he deviates, his deviation will give you the expected, this deviation will not affect the expected present value of the other agent's incentive terms. So the expected present value will be 0, no matter how he deviates. So agent I deviates, and we look at the incentive terms gamma j of agent j. Okay, so here's how we wrote it. So this is kind of the timeline, and the time goes. Agent j is getting this incentive payments. Okay, so this is before agent. So in the first period, before agent j observed his type, okay, he is getting minus gamma 1 minus. Okay, then after he observed his type, he is getting plus, gamma 1 plus. Okay, then he observed, then the types of the other agents are observed. Okay, then we get into the second period. Okay, agent j is charged minus gamma j2 minus, and then he gets gamma j2 plus, and so on, and times goes on, and in every period you have this minus gamma minus and plus gamma plus. Okay, and kind of when you add the so this is how you break it up. Now suppose agent I deviates. Now this is the independent type assumption tells us that even if agent I deviates, but he knows that agent j is being truthful and obedient, then agent I's deviation, his private history, his deviation will affect his private, history, but it's not going to affect his beliefs about agent J's type. Okay, so in other words, his beliefs about agent J's type will be exactly the same beliefs as what the designer has. So when he deviates, the designer kind of think of these payments as the payments are constructed by the designer taking expectations given some beliefs. So the beliefs of the designer will still be correct, even if agent I deviates. So I guess that's a better way of saying it. So agent I will not have any informational advantage over the designer about the evolution of agent J's type. Of course, he will affect it. He will be able to affect it, but the designer will know exactly what it is because the only effect is through the public decisions. Okay. So if agent J is expected to report truthfully, then basically by the law of iterated expectations, the expectation of gamma plus will be equal to gamma minus. Right? The only difference between gamma minus and gamma plus is that now we take expectation based on new information. But the new information is the report of agent J. Agent J reports truthfully. Okay, so therefore on expectation we know that the two terms have to be the same. So therefore they just cancel each other out on expectation. Okay, so the ex-ante expectation of this will be 0. Okay, and that basically shows that on expectation agent I that does not affect the total incentive terms of agent J. Then of course that's true in every period, you add it up and you get 0. Okay. Now, so this is a proof of claim 1, and then this was claim 2. Okay. Now the proof of claim 1 looks at the agent's effect on his own incentive term. And the claim says that for every possible deviation of agent I, the expected present value of his own incentive term equals up to a constant to the expected present value of the payments in the original mechanism. Okay, so here's basically the same kind of timeline for agent I. So first agent I is charged gamma 1 minus, then he observes, reports his type, and he is paid gamma 1 plus. Then the other types are observed. Then we go into the second period. Then agent 1 is charged gamma 2 minus, and so on and so on and so on. So you have, again, a bunch of these terms. But as you see, we'll have to group them differently now for agent I. So again, the independent types assumption is used because now we are taking expectation over the other agents. Agent I deviated, but again, his deviation does not affect. It's not true that it doesn't affect beliefs. Actually, it's not quite true. But basically, what happens is that he doesn't have any informational advantage over the designers. So the expectations that the designer uses are, taken with given the right distributions. So the beliefs of agent I, even though he deviated, will be the same as the designer's beliefs over the other agent's reports. Okay, and then if you think, so now you think about the, so this is the place in the first period where the other agents have reported, okay? And the other agents are reporting truthfully. And basically, again, we're taking expectation over of the same term, but the expectations are taken over the arrival of some information, and we know the correct beliefs about it, and therefore this is again the law of iterated expectations. It will tell us that these two terms on expectation will exactly cancel each other out. Okay, so the gamma plus. So again, we have canceling, but different kind of canceling. So gamma 1 plus cancels with gamma 2 minus. Yeah? Okay? So that is again, so remember all these gammas are taking expectations of the same thing, but given different information that we have. So now agent I deviated. Okay, so he deviated, but so this is now the report sent by the other agents. Okay, but even though he deviated, he has the same beliefs of reports of the other agents as the designer does. So we are using expectations. Okay, so then we're just taking expectations of the same thing. So this is the law of iterated expectations, says that an expectation, the expectations of the expectations have to coincide. So because you're subtracting this from this, you get 0. Okay.
So this is where you use the truthful reporting.
Yes, so the truthful reporting of the other agents is used, of course, right? Because both the designer and agent I assume that the other agents are reporting truthfully. Yes. Okay. So that's why you get this canceling. Okay. So basically everything cancels except, well, not everything cancels. So if you go, for example, up to period t and stop, if you only had a finite number of periods, so what would not cancel is the last term gamma plus and the first term gamma minus. So so just imagine you have first just to make it simple. Suppose you have finite horizon. So then you would just have this difference between the gamma plus t, and gamma plus t is kind of the expectation taken on period t. But of course, well, if period t is the last period, then it's not the expectation anymore. You already know exactly what it is. Okay, so this just will be the payment in the original mechanism. And gamma in the first period minus, this before any information is obtained, and this will be just a constant. Okay, because it's just expectation based on 0 information, it will be just some constant. Now of course, in the infinite horizon case, well, you just take t equal to infinity, and you will get this convergence. So that this last term will just converge to the net present value of payments in the original mechanism. Okay, and so what you get is you basically get the net present value in the original mechanism minus some constant. So which is what this claim says. So no matter how agent I deviates.
Mhm. Essentially no linkage between the periods. It's the same argument you gave in the example.
Well, I guess both claims have precedence in the example.
Right,
But
here you're using this.
so what do you mean by link? Yeah, I guess link. Well, the linkage you mean that we are canceling terms across periods. Yes. Right. So I guess I mean they're kind of similar arguments, and really the difference is that you're taking expectations. So the point is when you take so in both cases the argument is that when you're taking expectations of what others reports, the things cancel out because you're taking expectations correctly. But which things cancel out is different depending on whether you look at your own incentive term or at the incentive terms of the other agents. So when you look at here at your own incentive terms, then intermediate things cancel out, and you get exactly what you want. While when you look at the incentive terms of the other agents, then things cancel out within period, and then you get exactly 0, which is also what you wanted. Okay, so that's sort of the argument for the proof. Okay. So now I'll talk about kind of the application to games. Okay, so here you have an efficient budget balance mechanism, but we also use it to show some kind of a Fock theorem, so that even if you don't have any enforcer, you can sustain this as an equilibrium of the game. So in the game, there's no enforcer, so all decisions will be made voluntarily by the agents, including the public decisions. So both public and private decisions will be made voluntarily. And the payments will also be made voluntarily by the agents to each other. And the question is, can we sustain efficiency in a perfect Bayesian equilibrium? So the idea is that, well, we can try to do it by basically implementing this balanced team mechanism that we constructed, but in a way that everything is voluntary. Okay, and the way the mechanism will work is if there's no publicly observed deviation, as everything looks okay, then the agents are supposed to make these payments to each other, where basically the zijt is a payment that agent I makes to agent j in period t, which will just be the incentive term of agent j, and the terms are shared equally, so he is only paying 1 over n minus 1 share of this term. Of course, this is not guaranteed to be positive, so you have to maybe add some constant to it, ki, just to make sure that it's positive. So there's some constants that you have to play with. Okay, and then you have to say what happens if there are some publicly observed deviations. So what kind of, you can have publicly observed deviations that agent I just refused and didn't make the right payment. Okay, and another public deviation could be if there are some public decisions that have to be made. So for example, how much everybody should be fishing, but some agent deviated and didn't make the right public decision. Okay, so in that case, we have to switch to some punishment, and here we are not creative at all. We just say, suppose there is some belief-free Nash equilibrium that gives everybody 0 payoffs. Well, 0 is just a normalization, but just, of course, in general, if this is not true, you could imagine some kind of self-enforcing punishments as well. But here we don't talk about the problem of punishment enforcement. Just imagine there is a Nash equilibrium that gives 0 payoffs forever to everybody. Okay, so here you have sort of two problems. You want to prevent private deviations and prevent public deviations. So a private deviation, one that's not detectable, which is just like deviation in the mechanism, where you do something, you misreport your type, you change your private and observed decisions, but nobody knows that you deviated. And that, of course, is prevented, as we already proved. But now we have also the second problem is preventing public deviations. So Susan also called them off-schedule deviations, or can call public deviations, and you can think of public deviations as kind of call it quitting. So it's like you quit. You do something, but it's not just quitting. Of course, you can also, you can also benefit right away because you refuse to make the payment. And how do you prevent it? Well, you have to prevent it just by going to this 0 payoff Nash equilibrium. And the question is, can you do it? Well, you can do it if you can make sure that. Of course, you want agents to be patient so that the gains of future cooperation have to be high enough to induce them not to deviate. And you can play with this constant ki so that you can spread these gains, so that you can make sure that all agents are getting something out of this cooperation. But the challenge is there's one challenge though, okay? And the challenge is how big are these payments gamma jt? Right? We don't want the payments to be big, because the bigger are these payments, the more tempted the agents will be not to make the payments. Okay? So the challenge is to make sure that these payments are small relative to the total present value of the relationship. So how do we ensure that these incentive payments are small? Okay, that's sort of a substantial problem. So, and that's where we need an extra assumption. So it's not always true. We need an extra assumption to ensure that these payments are small. So of course they have to be small in a way that does not depend on delta, because we want to take delta to 1, and we want to make sure that even if the delta is close to 1, so that they're very patient, but these payments don't blow up in the process. So they still have to be bounded, even when delta is 1. Okay, now let's think about what these payments are and see how we can make sure they're small. Okay, so this payment, just remember how they're constructed. This is the change in the expectation of future utility. Well, because we're using the balanced T mechanism, the payments in the T mechanism are just the utilities of the other agents. Actually, it's a sum of over all the other agents of the changes in their future utilities. So now the little u's, these are flow utilities in each period. So what you do is you add up over all the future periods, and you look at how the current report. So you look at how the current report of agent J in period T affected the expected present value of the utility of agent K. So these are the payments. Okay, and of course the problem is that of course it's weighted by the delta, but when delta is 1, how do we make sure that this doesn't blow up? And if you think about it, you can see that the way we can ensure it is to say that the private information of agent J should have some limited effect on the future. So if the private information of agent J doesn't have a permanent effect on the future, if it sort of dissipates over time, then we'll be okay, because instead of just discounting by delta, we'll be discounting also by the effect on the future. Okay, so that in other words, you should have limited persistence in your stochastic process. Okay, and limited persistence will ensure that these expectations of the two things will become very close in the future. So they'll go to 0 fast. Okay, so that my current report will not have a big effect on the expectations of utilities in some distant future. Okay, and formally speaking, this is ensured by assuming that the stochastic process is ergodic. And ergodicity is exactly a property that ensures that the distribution in the future doesn't have much dependence on where you started. So as you go further in the future, the distribution becomes, converges to the steady state. Actually, it converges geometrically fast, and because of this geometric rate of convergence, these two expectations converge fast enough to each other so that the total present value is bounded even if you use if you put delta equal to 1 here. Okay, so it gives you a bound on these payments that is independent of delta. So this is a kind of formal statement of the theorem. So we assume, as usual, Fock theorems, now we assume that the action spaces, the type spaces are all finite, and that they are the same in each period. So now we also assume stationarity. So everything is the same in each period. That the payoffs are time separable, stationary, and that you have Markov type transitions. So we assume Markovness here. That you have independent types, private values. We assume that the stage game has a 0 payoff belief free Nash equilibrium, which we'll use as punishment. Okay, now we'll also use the concept of a Blackwell policy. Okay, so what's a Blackwell policy? So if you read about decision-controlled Markov processes, so what you can see, there's a theorem, not so hard to prove, is that there is a policy, there is a decision rule, or they call it a policy, that will be optimal for delta close enough to 1. So there will be an interval of discount between, some delta hat and 1, so that on this whole interval, And actually, it's not surprising because, in some sense, the set of policies is finite. And because it's finite, there will be some interval on which a given policy is optimal. So that's called the Blackwell policy. So it's optimal policy if you're sufficiently patient. Okay, so it always exists. Okay, so there's theorem that says it always exists. So we call it chi star. And so the assumption, though, that we make is that this policy chi star induces a Markov process with a unique ergodic set. Okay, so that no matter where you start, you will end up, eventually, that's the intuition, what's an ergodic set? You will end up in the set of states in which you will cycle, and the probability distribution of where you are will not depend in the limit on where you started. Okay, and so you get this. This is called the ergodic distribution, and the ergodic distribution will. The assumption that we do make is that it gives you a positive expected total surplus, so that there are some gains from cooperation over this belief-free Nash equilibrium. So under these assumptions, then for this discount factor close enough to 1, the Blackwell policy can be sustained in a perfect Bayesian equilibrium using this decentralization of balanced team transfers, where agents are making payments to each other. And the proof is basically kind of based on the intuition that I gave. Is that what ergodicity gives you is that the expected time average payoffs will converge geometrically fast to the steady state, regardless of the history, and that will ensure that the current reports, have a bounded effect on the incentive payments. The incentive payments are bounded, regardless of delta, and that will ensure that agents are not tempted to renege on the incentive payments. Okay, so conclusion. So we had this general dynamic model, serial correlation, and so on and so on. Decisions can affect distributions of types, and we constructed Bayesian incentive-compatible budget balance dynamic mechanisms. And there's a trick there is that use the incentive payments. There's only one trick. It took us a long time to get to that trick. So we started in a much more complicated way, but as usual, the simplest solution takes the longest time to find. But the trick is really the comparison to AGV. Instead of basing the incentive payment on the total utility, expected utility of the other agents, we base it on the change in the total expected utility of the other agent. Just one thing, we'll use the change due to the current report, and that turns out to be enough to work because it yields correct incentives for this player, but also prevents the opponents from manipulating the expectation of these incentive payments. And then we can satisfy participation constraints provided that the players are patient enough. Participation constraints is sort of like self-enforcement because it means that nobody wants to, make an observable deviation and go to break up the cooperation. And provided that you have this ergodicity property. Okay, so I want to say a little bit about what happens under different assumptions. So we talked about interdependent values already, and even in the static model, it doesn't always allow to implement efficiency. But if you can implement efficiency, then you can do budget balancing still the same way. Now with correlated types, just because you have correlated types, it doesn't mean that you cannot implement efficiency with balanced budget. Actually, generically you can. So this paper by Depremont, Kremer, McLean, that in the static model they say that also generically you can implement efficiency with budget balance, and it extends clearly to the dynamic model. I think there's a paper by Obara that does it. I'm not sure. I couldn't find the exact paper, but I'm pretty sure that he managed to prove it. Impatient players. Yeah, so I guess it was late last night when I wrote it. So. Okay, so of course, now what about participation constraints? Well, we know participation constraints in general cannot be satisfied. So remember the Myerson-Satterschweidt theorem. So in the static model, you can not guarantee that you satisfy participation constraints. Of course.
That's with balanced budget.
Yeah, with balanced budget. Yes, right, exactly. So here, in general, you cannot satisfy them, but the reason we could satisfy them is precisely because of the ergodicity assumption. So we need an extra assumption that basically makes sure there's enough gains. Future cooperation does not depend on the current, so the future does not depend on the current state too much, and that's what allows us to satisfy these constraints. Of course, if the types are fully persistent, then you're basically back into the static world. So you get non-ergodicity because the current type affects the future too much, and then you will not be able to satisfy participation constraints. Okay, now if you extend to non-quasi-linear utilities in general, you cannot implement Pareto efficiency, but yeah, I thought Atkins and Lucas is a kind of one interesting example of what you can do when you are interested in efficiency, but you have non-quasi-linear utilities in a dynamic setting. So, okay, so that's it. But have questions? Yeah.
Assumption that you can use zero payment and nobody leaves the as a function is actually pretty strong. For example, in your fishing example, it means that if someone deviates, then you don't fish at all. You don't do fishing at all.
No, well, I would actually say in the fishing example, it would mean that if somebody deviates, then we fish like hell. The fish has, basically it's a non-cooperative. So basically the idea is that it has to be a bad outcome, right? Yes, okay, you're right. So if you don't fish at all, it is a bad outcome, but you cannot sustain that. Yeah, so but I would propose instead of that, you'd say, if some deviates, then we go towards a lot of fishing. But does it really give zero payoffs? Well, I'm not sure, but you could imagine that, if you do a lot of fishing, eventually the fish disappears, and it's almost as bad as zero pay. I mean, of course, zero is just a normalization. Doesn't mean that it's exactly zero. But what makes it easy for us is that it does not depend, it doesn't have to be exactly zero, but it has to be something that's bad and really does not depend on what people do. So I think if you replace, but I think basically if you replace zero payments with some kind of non-cooperative equilibrium that is bad, the only complication is that you have to keep track that when you deviate and then it affects the subsequent equilibrium, it just makes it technically a little more complicated. But I'm pretty sure that it will still be true that if you say, when somebody deviates and you switch into some kind of very bad equilibrium, even if it is, it's not a belief-free equilibrium, it's just harder, you need to keep track of what you believe about each other to make sure how much you fish and so on. But I think it would still work pretty well. I didn't do it, but I think, if you think that just non-cooperative fishing is probably a very bad idea. So you think that, I think it would work as punishment. Okay. Thanks. Yeah. Okay.
Thank you.
Thank you.